This is the second lecture of a Physics 11 course based on the Ontario curriculum. The subject is how to measure with an analog instrument. These devices require a comparison of the level of a liquid or the hand position to some calibrated markings. Examples of such instruments are a typical clock, a measuring cup, or a ruler. We will use the example of a ruler to illustrate how to derive a measurement from it. Here is a zoom-in version of a ruler set beside a length to be measured. The markings on the rulers are 1 millimeter apart. The numbers are shown in centimeters. The end of the line underneath appears to be between the markings 4.6 centimeters and 4.7 centimeters. Just like a digital instrument, an analog instrument does not have infinite precision. Measurement will involve establishing a best estimate and a measurement error. The separation between the adjacent markings is the smallest increment, and the measurement error will be, just as with the digital device, half of the smallest increment. Here the separation between markings is 1 millimeter, so the measurement error is 0.5 millimeter or 0.05 centimeter. Now on to the task of establishing the best estimate. The reason for choosing the middle of the range for a digital instrument was that no number between the numbers that the instrument could display was more likely than the others to be the real unknown quantity. This is not the case for an analog instrument. We have a visual clue. It is the experimenter's responsibility to use that information to add an extra decimal to the number associated with the lowest marking. In our example here, the length to be measured is clearly more than 4.6 centimeters, but has not reached the middle of the gap between the markings. An extra decimal could be 3, if you estimate that roughly 30% of the gap has been covered in excess of the length of 4.6 centimeters. This would give you a best estimate of 4.63 centimeters. There is no point in trying to add more decimals than that. The digit 3 is already uncertain and at the limit of what you can propose. Our final measurement could be coded as 4.63 centimeters plus and minus 0.05 centimeter. If the length you wanted to measure had been aligned, as far as you could tell, with the marking 4.6 centimeters, then the extra digit to add would have been 0 to reflect that fact. The best estimate would have been written as 4.60 centimeters. The previous example has shown you that the number of decimals that you use to express your estimates is meaningful, and it must reflect the information that you know and that you want to convey. No more, no less. When an estimate is written with only the digits that reflects the amount of information that you want to convey, it is said to be expressed with the proper number of significant digits. All the values of the best estimates and of the measurement errors evaluated so far have been expressed with the proper number of significant digits. In order to continue to do so, you have to know what a significant digit is. A significant digit is any digit in a number except a string of zeros to the left of that number. The reason why a string of zeros to the left is not significant is because you can make them disappear by using a power of 10 or by changing the measurement unit. If you take the number 0.06040 meter, for example, the 2 zeros to the left can disappear by using the factor 10 to the minus 2, like in 6.040 times 10 to the minus 2 meter, or by using centimeter instead of meter, like in 6.040 centimeters. Please note that the 0 between the digits 6 and 4 is significant, and so is the 0 to the right of the number. However, there are situations where a string of zeros to the right is considered non-significant. Those situations involve integers, like when dealing with a population count. A population of 250,000 is written with only 2 significant digits, not 6. This exception makes it tricky to deal with quantities that are not integers in general. The integer 100 kilogram, according to this exception, has only 1 significant digit. If you want to express it with 3 significant digits, you need to use decimals, like in 1.00 times 10 to the 2 kilogram. To avoid this ambiguity, use numbers with decimals. Let's do an example on how to express numbers with a given number of significant digits. All the digits in 124.7 centimeters are significant, so the number of significant digits is 4. If you had to express this quantity with 5 digits, you would just add a 0 to the right, 124.70 centimeters. With 3 significant digits, you would need to round up to 125 centimeter because the next digit, 7, is above or equal to 5. Finally, this number expressed with 2 significant digits could be written as 1.2 times 10 to the 2 centimeters, or 1.2 meter because the next digit, 4, is below 5. Now that you know what a significant digit is, let's see how it applies to how many digits you should use to express your measurement error. Remember that a quantity expressed with the proper number of significant digits only conveys the pertinent information. What do we need from a measurement error? The purpose of a measurement error is to give a rough size to the uncertainty surrounding our best estimate. With that in mind, there is no need for loads of decimals. A measurement error of 0.3481 centimeter is not useful. The relevant information is that it is roughly 0.3 centimeter. It is customary to express a measurement error with no more than 2 significant digits. In this course, we will limit our number of significant digits to 1 for the measurement error. For example, a measuring cup with markings that are 50 milliliters apart would have an increment of 15 milliliters. Dividing 50 milliliters by 2 leads to 25 milliliters for the measurement error. 25 milliliters has 2 significant digits. To reduce this number to 1 significant digit means that 25 milliliters is rounded to 30 milliliters, preferably expressed as 3 times 10 milliliters or 0.03 liters. The advantage of letting our measurement error have only 1 significant digit is that we know which decimal position in our best estimate is affected by the error. The best estimate should not have more decimals beyond the last decimal position of its error. It should not have less decimals either. In fact, best estimates are written up to the same decimal position as their measurement error. Recall the measurement of the length at the beginning of this lecture. You can see that both numbers end on the same decimals. It means that a best estimate expressed with the proper number of significant digits gives information about the rough size of its measurement error. The smallest the measurement error compared to its best estimate, the more significant digits the best estimate has. If you compare a best estimate of 2 kilogram with a best estimate of 2.00 kilogram, you can tell that the second value was obtained with a more precise instrument. Now that you know how to measure, how would you use these measurements in calculations? This will be the subject of the next installment.